All right, welcome to Etale Cohomology on October 20th, 2020. Before we start, maybe a brief warning. I didn't sleep well last night, so I might be a little lower energy than usual, and my apologies if so. All right, so now that we're recording, are there any questions about the material we've covered previously that you guys want on the record? All right, if not, let's get started. So last time, we started talking about étale pi 1. So let me just remind you the definition in the main theorem. So here, so X was a scheme, which I took to be locally Noetherian. Today, I'm going to only state things for varieties over fields. So X will always be a normal variety over a field K. And that's just because a lot of the interesting, well, okay, that's not strictly true. There will be one situation when I consider a variety over another base, but I'll tell you when. So we defined the category finite étale of X to be the category of, so the objects are y to X finite étale, and morphisms are morphisms over Y. Or sorry, over X. And then given a geometric point, X bar mapping to X, we defined a functor, Fx bar, from finite étale of X to sets, or really finite sets, given by sending finite étale X scheme Y to the fiber over X bar. And maybe it's worth remarking, I mean, here X is a variety over K, but this geometric point doesn't have to be spec K bar, right? It could be, for example, you could take an algebraic closure of the generic point of X, or of the residue field of the generic point of X, so the fraction field of X, and map that to the generic point, and that's a perfectly good base point for a fundamental group. Okay, and then finally, what we defined was we defined the étale fundamental group of X bar to be the automorphism group of this functor Fx bar, which we called a fiber functor. And last time we talked about a couple examples. So we talked about the case where X was spec of a field, in which case this recovered the absolute Galois group. And this choice of geometric base point is the same in that setting as the choice of algebraic closure of your field. I claimed that there was a comparison theorem to the in the case of varieties over the complex numbers to the profinite completion of the usual topological fundamental group, and I'll explain why that's true today. And then I also gave you an example in characteristic P. I began the sketch of the fact that the fundamental group of the affine line over a field of characteristic P is not topologically finitely generated, and today I'm going to finish the proof of that. All right. So before I continue, are there any questions?
I mean, this might come up later, but I was just wondering if there's nice ways to sort of relate the fundamental group while taking different base points.
Yeah. So we'll talk about that. So let me tell you what some of the fundamental theorems are. Okay, so theorem. So the first fundamental theorem is in SJ1. I'm not going to prove most of these. I'll prove a couple kind of selected theorems. So the main theorem is that that there's an equivalence of categories. So Fx bar is a map from finite étale to set to finite sets, but it's to finite sets with a pi 1 étale action, right? If you have any object of in the image of this functor, well, we have pi 1 étale acts on it, right? Just by the definition of what it means to be an automorphism group of a functor. So really this this maps to finite pi1 étale sets. And moreover, we discussed the topology on pi1 étale last time, and it was defined to be the coarsest topology so that that action was continuous. So we really get a functor to finite continuous pi1 étale sets. And the theorem in SGA1 is that this is an equivalence of categories. So I'm not going to prove this. The content in this normal setting is more or less just the fundamental theorem of Galois theory, and some Zariski's main theorem. It's we more or less just work with the Galois group of the fraction field. So are there any questions about this statement? So this theorem will be the main tool we're going to use. It's not formal. It's really a statement about schemes or about varieties over a field. Well, it's true in pretty vast generality, but I'm just going to take it as input today. So are there any questions about that? So are there any questions about what the statement means? Okay, so with that, I want to deduce a corollary, which I sketched the proof of last time. So corollary is that if we take A1 K, where here the characteristic K of K is not finitely generated, is positive rather, then A1K, pi1 étale of A1K x bar, for any choice of x bar, is not topologically finitely generated. And we sort of began the proof last time. So last time we observed that H1 of A1K with coefficients in FP is not finitely generated. And the claim is that there's a natural map from continuous maps, pi1 étale, to FP to H1 A1 FP. So this is étale cohomology with FP coefficients. And the claim is that this map is an isomorphism. Okay, so can anyone tell me what is the map? So how does one go from left to right here? How does one go from a map into FP to well, what is this thing? This is FP torsors, locally split in the étale topology. Any thoughts?
So an element of the left should correspond to an FP cover? Like a cover?
Yeah, that's right. So the element, well, an FP torsor is just the same thing as an FP étale cover after this representability statement we gave earlier for torsors for finite group schemes. So somehow we have to say that the left-hand side is also the same as an FP cover, FP Galois cover. So how do we do that? Well, the point is that FP acts on itself by addition, right? So like given an element of FP and an element of FP, you can add them together to get another element of FP. And what this means is that there's a map continuous pi1 étale A1, or really this is true for any scheme, to finite continuous pi1 étale sets such that the action factors through a map pi1 étale A1K to FP. Well, I mean, this is almost tautological. So all I'm saying is that a map to FP coupled with this choice of action of FP on itself gives you an action of pi 1 étale on FP. Do you guys agree with this? Great. Okay, and then by the theorem, those things are the same as FP choicers. A finite set with a continuous action by pi 1 étale is the same as a cover. If the action in fact is through FP, well, there's a little check. You have to check that it's an FP choicer. All right. So that completes the proof of that theorem. We also have the following corollary, which I think answers Ollie's question. So corollary, so for any x1 bar and x2 bar geometric points of x, pi 1 étale, x1 bar is isomorphic to pi 1 étale x2 bar. All right, so this is not entirely trivial from the theorem, and so maybe a note is this uses the assumption that x is a variety. In particular, it uses this theorem here uses the assumption that x is connected, and so otherwise this is untrue. If you like the definitions all make sense for disconnected x, but then what you get will honestly depend on x1 and x2. Just like in topology, you'll just pick up the fundamental group of the component that x1 lives in. Okay, and the proof is that the category. So step 1 is that the category of pi 1 étale x1 sets is going to be equivalent to the category of pi 1 étale x2 sets. Anyone? Why? Can anyone tell me why that's true? Well, it's because they're both equivalent to the category finite étale for x. Do you guys agree with this? This was precisely this claim over here, or this theorem. Okay, great. Thank you, Arvin. Okay, and then 2, this is not a non-trivial exercise. So the category determines the abstract group. The abstract group. Okay, so this is a weak form of what's actually true. So what's actually true is that there's an isomorphism, not just an abstract isomorphism, but rather one that's well defined up to inner conjugation, just like in topology. So in topology, if you have 2 base points, you can choose a path back and forth, and conjugating by that path gives an isomorphism between your 2 fundamental groups. So let me just briefly explain. So the remark is that in fact more is true. So in fact, this iso is well defined up to inner conjugation. Up to inner conjugation. So just like in topology, if you pick 2 different paths between your base point, what you would get by conjugating them differs by conjugating the loop given by going along one path and then back along the other. And so to actually choose an iso, you need to choose a path between these 2 points. So what do? So to choose an iso, you choose a sequence of specializations and generalizations. Of specializations and generalizations So let's say x1 goes to y1, which is a specialization of y1, which specializes to y2, which is a specialization of y3, which specializes to y4, and so on, and then finally, which specializes specializes to x2. So do you guys know what I mean by a sequence of specializations and generalizations? Does anyone have any questions about what I mean by this? All right. Maybe I should ask, what are your questions about what do I mean by a sequence of specializations and generalizations?
I think this question in chat.
Someone's in chat. So what does generalization mean? Oh, great. Thank you, Freddie and Jose. Yeah, so what I mean by this is, so these are points of a scheme. So this wiggly arrow means that x1 is in the closure of y1 and y2 is in the closure of y1. And here y3 is the closure of y3 contains y2 and y4 and so on. So this is a scheme theoretic analog of a path. So you go you take a point of larger height and then another point in its closure and then another point of larger height and so on and so forth. Does that clear things up, Freddie and Jose?
If we're working with connected stuff or irreducible stuff, then why can't we just generalize once to the generic point and then specialize?
You can. That's fine. Yeah. Yeah. That's. But I'm saying one makes a choice like this, and you made a choice, but it's not a. I mean, I guess it's a pretty canonical choice, but it's not. I don't know. I mean, the issue is So these are all geometric points. So that's a pretty canonical choice, except that you had to choose an algebraic closure of the function field of your variety, which is pretty non-canonical. Does that make sense, Arvin? But that's absolutely something you could do.
And so when you say choose an algebraic closure, do you mean choose an embedding of the function field into an abstract algebraic closure?
Yeah, but it's also just in general, the construction of algebraic closures is not a functor. There's no, given a field in general, there's no canonical way to make an algebraic closure. So anytime you choose an algebraically closed, sorry, I'm using kind of circular language, but anytime you have a field, there's not a canonical way of embedding it into an algebraically closed field unless it's already algebraically closed.
I see. Okay.
So people who are sufficiently functor pilled will always say choose an algebraic closure. Is that okay?
Yes, thank you.
Yeah. So given this, then the claim is that so once having chosen this, the necessary claim is that so if x bar specializes to y bar, then you have a diagram as follows: finite étale x, then we have fx bar set, fy bar set, and then a map like this, making the diagram commute. Okay, and then this map here is what's going to induce this actual isomorphism over here. Okay, and can anyone tell me, so what is this map? So how do I go from a fiber over x bar to a fiber over y bar? Sorry, I'm being, what I really mean is there's a natural transformation. Sorry about that. So what I mean is there's a natural transformation like this. So how do I go from the fiber over x bar to a fiber in its specialization? An element of a fiber over x bar, sorry, to an element in the fiber over its specialization. So let me call this natural transformation eta. So eta of y over x, and now of a point in the fiber, so let's call that little y. Oh no, I'm already using little y, sorry. let's call that little z, is what? Anyone? So maybe let me draw the picture, if that'll help. So here's some kind of étale cover of some base x. And then I have a point here x, which specializes to a point y. And a fiber over x, an element of the fiber over x. And I want to construct an element over the fiber over y. How do I do that?
Yes, we specialize the fiber over x, the fiber.
Yeah, so exactly. So you take the closure of z and then intersect with the fiber over y. Okay, and that's a geometry point. Does that help? Or is that clear what this means? Great. Okay, so what this says is, so this is a more precise version of the corollary. It says that if you choose a path like this, so then you get a choice of isomorphism. Great. Cool. So does that answer your question, Ollie, about base point independence?
Yeah. I just wanted to really know what the analog of a path was. Sort of.
Great. Okay, so now let me state a theorem we used in examples last time, and I'll say a word about the proof. So this is what I would call a comparison theorem. So if x is normal over C, then there's a map from pi1 étale x bar. There's a map to it, sorry, from pi1 of the analytic space associated to x with coefficients in the analytic, the point corresponding to our base point here. X actually has to be a C rational point for this to make sense. So there's a map like this, which induces an iso after profinite completion. So it induces an isomorphism from the profinite completion pi1 étale x bar. All right. So can anyone tell me where this map comes from? Oh, sorry, Ollie. There's the weird ambient sound is the intake vent for my heater is right under my desk. Is it incredibly annoying?
It's fine. It's fine.
Okay. If you guys are having trouble hearing me at any point, let me know. All right. So can anyone tell me where this map comes from? So my hint is that the existence of a map like this means that given a finite pi1 étale set, we get a pi1 set for the usual pi1. So and I claim we can go the other way. So how do we go from a finite pi1 étale set to a pi1 xn set? So okay, so let me maybe write some stuff down. So first of all, pi1 étale of x bar is just by definition the automorphism group of the functor fx bar. The theory of covering spaces tells us that the usual topological pi1 of xn x bar n is the automorphism group of the functor, which I'll call fx bar n from covering the category of covering spaces to set. So these covering spaces are not necessarily finite covering spaces. So the claim is that, so it's enough to show that well, there's a functor called n, which we discussed when we grouped Arden comparison. It's enough to show that we have a diagram as follows. So f étale cover X, and then this maps via fx bar to set. This maps to fx via x of bar. Yeah, so we have a diagram like this. So enough to show that we have a diagram like this which commutes. I'll call this, we already know what this functor is. It's analytify. So given a finite étale x scheme y, we can analytify it to get a covering space of xn. So it's enough to show we have a diagram like this that commutes, and that n induces an equivalence between the category finite étale and the category of finite covering spaces. All right, let's take, well, maybe I'll finish this proof and then we'll take a 2-minute break and I'll try to get this noise to stop, because it's also bugging me. All right, so can anyone tell me why this is true? So why do we have an equivalence like this? Okay, so the answer is the Riemann existence theorem, which is precisely the statement that analytification induces an isomorphism like this. And this is a non-trivial theorem in analytic geometry, so I'm not going to prove it. All right, I'm going to pause for a second and try to get this noise to stop. I'll be right back. All right, I'm back. I think that worked. Did it? Does the sound seem to have gone? Great, amazing. All right, are there any questions about this quick sketch of the comparison theorem? So maybe let me say a bit more, because I feel like I'm very rapidly translating between the categories of covering spaces and the category of G sets. So what did we show? Well, really, I just said the words Riemann existence, but what does Riemann existence show? It says that a finite étale cover, aka a finite continuous pi1 étale set, is the same as a finite analytic cover, aka a finite analytic pi1 set. So what does that mean? It means that an action of this on a finite set, a continuous action of this on a finite set, is the same as a continuous action of this on a finite set, which means that this is the universal object through which an action of this on a finite set factors. Okay, and that's another definition of the profinite completion. All right, so this is this leads us as a corollary to a lot of computations. So for example, if X is a smooth proper curve of genus G, the étale fundamental group of X, this is over the complex numbers, the étale fundamental group of X is generated by elements A1, B1 through AG, BG, subject to the relation that the product of the commutators equals 1. And then the profinite completion of that. And what's the proof? Well, you do the topological computation, and then you take the profinite completion. Okay, and there's no other known proof of this fact. This is a fact without an algebraic proof, as far as we know.
Where did the profinite completion come into play on the complex side?
Yeah. So the point is that what are we saying? We're saying that a set with an action of this is the same as a finite set with an action of this.
Mm-hmm.
Right. So that the group with that property is the profinite completion of this group.
Okay.
Yeah. Does that make sense?
Okay, so on the pi1 étale side, we were not just looking at finite sets; we were looking at any sets, and then
no.
Oh no, so sorry, the other way around.
Yeah, that's right. Yeah, here the covering of X is all covers of X.
Okay, I see.
Great. Cool. Yeah. Okay. So this gives us a computation. All right, what if we're not over the complex numbers? So let me state a theorem. I'm not going to prove this. I'll just say what the maps are, but I'm not going to prove. There's an exactness statement, which I'm not going to prove. So recall that X was a variety over K. So that means we have a map from X K bar to X, and then X is a variety to K, which means it maps to spec K. And this diagram induces a sequence of maps. So first of all, the étale pi1 of xk bar with coefficients in x bar. This maps by functoriality. So a geometric point of x bar gives you a geometric point of x. So you get a map just to the usual fundamental group of x with the same base point. And while a geometric point of x gives you a geometric point of spec k just by mapping down. And so you get a map to the Galois group of spec k, which we said last time was the absolute Galois group of k. And the claim is that this is a short exact sequence. Okay, so what is the content of this claim? I'm not going to give a detailed proof, but for example, the content of the surjectivity of this map is that if you have a cover of K, so a separable, if you have a connected cover of K, so a separable extension of K, it remains connected when you base change to X, and this followed from the assumption that X was a variety. So here, for example, so surjectivity, so maybe proof remarks. So for example, here, surjectivity follows from geometric connectedness of X, which followed from the running assumption that X was a variety. Yeah. Or what about exactness in the middle? So that turns out to be the statement that if you have a connected étale cover of X, it becomes disconnected when you base change to xk bar, if and only if it had a piece pulled back from an extension of K. Meaning it's a characterization of what covers are geometrically connected. Great. Are there any questions about that? So I'm not going to give the proof. It's actually pretty non-trivial. Great. All right, so I want to talk about a little bit about how to compute in positive characteristic. So I want to talk about specialization maps. So what's the setting? So now I'm going to assume that that X is proper and flat over a complete DVR. DVR with geometrically connected fibers. Okay, so I've now dropped the assumption that we have a variety over a field, yeah, so I'm going to state a theorem in this generality. So the theorem is that, so maybe let me give the DVR name. So the DVR is R, and then I'm going to say that I'm going to let K be the fraction field of R, and little k be its residue field. So R mod the maximal ideal. So the theorem is that so given a geometric point, so X bar on the special fiber, so X little k, the natural map from the Etale fundamental group of the special fiber with base point our geometric point, well, the special fiber maps to the whole space, right? It maps to pi1 of X at the same base point. And the claim is that this is an isomorphism of topological groups. All right, so can anyone tell me why this is true? This is a very non-trivial theorem. So what do we have to prove?
This is like if you have an étale cover of the special fiber, then you can sort of extend it to an étale cover of the whole thing.
Yeah, that's right. So you have to show that the categories of finite étale covers are the same. So what you need to show is the category of finite étale covers of X. Well, there's a restriction functor. So that's just base change to little k, to the category of finite étale covers of xk. You have to show that this is an equivalence of categories. So this is the goal. All right.
What
So
I said not sufficient?
I'm sorry?
What I said is not sufficient to show that every étale cover of
I mean, I think that's the content of the goal. Yeah. Right. That's essential surjectivity.
right.
But then you'd still do need the fullness and faithfulness, but that's the content of those is much easier. Yeah, so let's just as a sketch. So maybe let me just prove essential surjectivity, and then the other stuff is the proof you'll see is going to be more or less the same idea. So okay, so why is this map essentially surjective? Why is this functor essentially surjective? So in other words, given a finite étale cover of X little k, we want to make a finite étale cover of X. And the picture you should have in mind, by the way, and I think this is a good picture to have in mind in general, is a family over a DVR. So X over DVR is like a family of varieties over a disk. And in that situation, the family will retract onto the central fiber. So in topology, if you have a nice family over a disk, it's going to be homotopy equivalent to a central fiber, as long as you take the disk sufficiently small. All right. So why is it essentially surjective? So step one is given a finite étale cover. So Y to xk finite étale, we want to construct. Well, step one will be not to construct a finite étale cover of X, but a finite étale cover of the formal scheme obtained by completing. So this is the completion of X at the maximal ideal of the base M, which is going to be finite étale. All right. So how does one do this? So here, I guess we need a little digression on deformation theory. So we need a little digression on deformation theory. So in general, so what's the situation? Well, we want to lift y over x mod m to the n, where m is our maximal ideal. So we're going to do that one n at a time. So the situation we're in is we have, let's say we have y to, let's just do the first step. So we have y to xk, sorry, that's a curly x, and this maps to x tensor r mod m squared, right? And then we wanna fill in this diagram with something like this, and we want to understand the uniqueness and existence properties of that question mark. Do you guys agree that this is kind of the first step of what we want? And in general, let's say we have like a yn over, let me write it this way, over x tensor r mod m to the n. Well, this lives inside of x tensor r mod m to the n plus 1. And we might want to fill in this diagram. Okay, and let me just call the ideal. So let me just call the ideal defining this embedding. So let's call the ideal defining this embedding I is the ideal defining this embedding.
Can you see what these might correspond to in that picture you described over the punctured disk?
It's not. It's sort of infinitesimal thickening. So it's you have your central fiber. You thicken it infinitesimally, and then you try to, if you have a cover with the central fiber, you're trying to lift it to that infinitesimal thickening. But it really is an infinitesimal object. It's not something you can see pictorially, really. Does that help, Arvind?
Yeah, I just wish I could visualize infinitesimal thickenings. So.
Yeah, it's I mean, I like to think of them as little arrows sticking off of the central fiber or something.
I see.
But
that's the picture I've seen, and I've always just been confused. But okay, cool. Thank you.
I mean, I think this is really an algebraic object. I don't think it's really I don't think there's really a picture. Okay, so the so the general principle in deformation theory is that there's the existence of an object like this, so meaning the existence of a question mark here, making the diagram Cartesian, and so that this map here is flat. Is the existence is controlled by an obstruction class, which usually lives in some kind of H2, and if a question mark exists, the set of them is a torsor for an H1. So I'll tell you what happens in this case. So there's an obstruction class, which lives inside of H2 of, it just ends up being, it lives in X2 of the special fiber xk with coefficients in omega 1 y over xk, so the first step, and then against this ideal sheaf I. So this is where the obstruction lives. And then the statement is that if the obstruction class equals 0, and I'll say a word about where this obstruction class comes from in a second. So if this obstruction class equals 0, then there exists a question mark flat, maybe I shouldn't have used question mark here. There exists yn plus 1 flat over X tensor R mod M to the n plus 1, making the diagram Cartesian. Arvind, if it makes you feel better, I'll say in a word at the end of this proof, like what topologically the whole proof kind of corresponds to. It does really mean something. So there exists a yn plus 1 flat over this thickening, making the diagram Cartesian, and then the set of such. So the set of such yn plus 1 is a torsor. Or I mean, the set of such yn plus 1 up to isomorphism is a torsor for x1 of the same sheaves. Okay. So does anyone notice anything about these groups? So y over xk was étale. So what does that tell you about omega 1?
They're 0.
Yeah, so both of these groups are 0. I mean, so this fact I wrote from deformation theory is true for an arbitrary smooth map here. Étale maps are smooth, so we're in this situation. So let me write étale here. And in that sense, in the smooth setting, these groups definitely don't have to be 0, and they often won't be. But in the étale setting, what does this say? It says the obstruction vanishes. And so there is a yn plus 1 here, and it says it's a torsor for the 0 group. So there's a unique one. Okay. And then the exercise from the conormal exact sequence is that yn plus 1 over X tensor R mod M to the n plus 1 is étale. So you could do this using the conormal exact sequence, or just using that you can check étaleness on the special fiber of a flat map. Great. Okay, so that was step 1. So what have we done? We've given a cover of the special fiber. We've made a cover of this formal scheme. So we've finished step 1 because we've made lifts through each step, and in fact we've shown there's a unique cover. Okay. So if you think a little bit for a second, that this same argument will give you faithfulness. All right, you'll need to look at x0 in that case also. All right, so now that we've constructed a cover of the formal scheme, how do we construct a cover of X itself? Oh, and Bob asked, why are the X groups 0? The X groups are 0 because these sheaves themselves are 0. So this sheaf is 0, and this sheaf is also 0 because Y was étale. Does that help, Bob?
Yes.
Great.
Yes, thanks.
Yeah. All right. So now step 2 is so we have a cover now. So we have in fact a unique Y to X hat completed at M, lifting Y, YK, or lifting our original Roman Y, I guess. And now we want a Y just covering X itself. All right, so how do we get that? So maybe one thing to note is that we haven't actually used properness here.
Can you use formal Gaga or something like that?
Yeah, exactly right. So this is just immediate from formal Gaga. Okay, which really needs properness. Okay, so I claim we've now proven modulo this deformation theory stuff and modulo formal Gaga, which is also quite involved, that this functor is essentially surjective, and you guys should try using it's more or less the same techniques. You should try proving faithfulness and fullness. Great, so maybe let me just say a word about where these obstructions come from. So the way one proves these theorems is via check cohomology. So first of all, you have to show that locally on X, you can find lifts like this. So that's some variant of the definition of formal smoothness to prove that. Or you can say like X itself. Yeah, so it's a little harder. No, sorry, that's not really an issue. So yn here, this is some smooth map. So locally it looks like affine space, and then locally you can lift affine space. Maybe that's the easiest way to say it. So that uses the structure theorem for smooth morphisms. Okay, so now what you have to do is you have to try to glue your lifts together. Okay, and that's not so hard. So locally, it turns out the lifts are unique, right? So you pick some isomorphisms between them. So unique meaning there exist isomorphisms locally between these lifts. So you pick some isomorphisms between them, and now the problem is they typically won't satisfy the cocycle condition. And then, okay, now this is a non-trivial computation. The failure to satisfy the cocycle condition will be an element of an H2, and really it'll be a check cocycle representing a class in X2. Okay, so that's where this obstruction comes from. And now, given that obstruction being 0, you have to figure out, okay, well, now how many ways are there to glue? And the gluing data will be acted on by check cocycles for this group. All right. Sorry, that was my very, very brief summary of all of deformation theory, basically. Great. So I claim we've proven this theorem. So what's the corollary? So the corollary is that given X, so given X as above, so this was, excuse me. So this was X as above means proper and flat over DVR. And let's say, suppose we're given an eta bar to X capital K, a geometric point of the generic fiber, specializing to some C bar in the special fiber, we get a specialization map. So we get a map I1 étale X K X bar to I1 étale X, sorry, this is a eta bar to X little k C. Sorry, my C's are so bad. Okay, and the proof, so what is this map? So this is the corollary is the existence of a canonical map. So the proof is just a definition. This isn't really I shouldn't call this a corollary, it's really a definition. So the corollary is that the proof is just that X K eta bar maps to X eta bar. There's a map of pairs like this. So we get a map I1 étale X capital K, sorry, this is a capital K, eta bar to I1 étale X eta bar. And now we said that we had when I was describing the étale analog of a path, I explained to you that if you had one point in the specialization of another, you get a specialization isomorphism between fundamental groups. So this gives you isomorphism to the fundamental group with the base point, this C bar. Okay, and now this we just showed is actually isomorphic to I1 étale of X little k C bar. Okay, so this is the map, this composition. So all it comes from is just including the generic fiber of our family X into X, and then using the X is the pi1 of X is the same as pi1 of the special fiber. Are there any questions about that?
And this map in general won't be an isomorphism or anything.
In general, no. It will very rarely be an isomorphism. So the theorem is that if X is normal, So let me call this map SPA for specialization. SPA is and I'm keeping all the running assumptions. So in particular, X is proper. SPA is surjective. Okay, and the proof, the content of the proof. So the content is that so given y to x finite étale with y connected, then yk is also connected. Great, and this just follows from Zariski-Nagata purity. The proof is just that y is the normalization of x in the function field of y, and so now you're done. The function field is so you're connected if and only if the function if yeah, you're done because the function field is domain. That's another way to say it. Okay. Great. So we have this surjective specialization map. All right. So are there any questions about that?
Can you give an example to keep in mind, maybe?
Yeah, sure. I'm about to do that. So let me maybe briefly make one more state one more theorem. So the theorem. So maybe this is a corollary. So again, we have x is normal. So and then over normal, let me just list all the hypotheses: flat and proper over R, and then we have eta and c as above. Then we can pass to the geometric fibers. So we can look at the pi1 étale of the geometric generic fiber. And this just the same construction will mean that this maps to pi1 étale of the geometric special fiber. And this is also surjective. Okay. Yeah, maybe before I give you an example, Arvind, I need to say one more theorem, and then I'll be ready for examples. So finally, the theorem is that if x is a variety over k, which is algebraically closed of characteristic 0, and then L over k is an extension of algebraically closed fields, then we have an induced map from, and I'll suppress base points, pi1 of xl to pi1 of x. And this is an isomorphism. Okay, and here the proof is Galois descent. So the content is one has to show that any étale cover of XL is actually pulled back from an étale cover of X. And this follows, for example, from the rigidity of étale covers in characteristic 0. Okay, so finally now I can give you some, are there questions about the statement? I mean, this is not a trivial statement, but are there any questions before I move on? And maybe a notice that we already know this is false in characteristic P. We saw it was false for the affine line. So maybe this is taking a lot longer than I expected. So maybe I'll make this an exercise. It is doable. But it's not trivial. And you guys should try it and ask me about it on Thursday if you are having trouble. Okay, so now we can give some examples. So here's an example. So suppose X is a smooth proper curve over an algebraically closed field of characteristic P bigger than 0, then the étale pi1 of X with any base point is topologically generated, by at most 2G elements. 2 times the genus of X elements. So can anyone tell me why this is true? So we now have enough to prove this fact.
Is it like we need one generator for the special fiber, and then?
Well, here we don't have a family over DVR yet. But you're right, we're gonna have to use this specialization stuff. So how are we gonna use it?
Like use Wood vectors or something like that.
Yeah, so step 1 is you lift to characteristic 0. So here we again have to use deformation theory. So we use the obstruction to deformations is given by an x2, but on a curve x2 with coefficients in some, so x2 with coefficients in some vector bundles will always vanish by Grothendieck vanishing. So you lift to characteristic 0 and then algebraize using formal Gaga. And then now we have a surjective specialization map. From pi1 of the geometric generic fiber of our lift to pi1 étale of X. And now this we can compute over the complex numbers. So what do we have? We're over some algebraically closed field. So for example, the algebraic closure of the Witt vectors. But our X is always defined over some finitely generated, the algebraic closure of a finitely generated subfield, which we can then embed in C. And then this theorem guarantees us that pi1 doesn't change under that action of descent to the algebraic closure of a finitely generated field and then embedding into C. So this we can compute using our comparison theorem. And then we know the fundamental group of a curve over the complex numbers is topologically generated by 2G elements. So now we're done by the surjectivity of this map. Okay, so again, I mean, this is the kind of thing this is the kind of technique that you have to use. It's the only way we really know to get at fundamental groups of varieties in characteristic P. All right, are there questions about that?
Is it false if X is singular?
Is what false?
The fact that it's generated by 2 elements.
Or two times the genus.
Yeah, sorry, that's what I meant.
Yeah. So for example, if you take a nodal cubic, so this is genus 0. Well, maybe I should ask, what do you mean by genus?
Well, let's
So for
take
geometric genus. So for arithmetic genus, I would have to think about it. It is probably still true, actually. Let me think for a minute. Yeah, I think for arithmetic genus, it's still true. So in fact, for arithmetic genus, I think, let's say if you're a nodal curve, I think 2G plus the number of nodes will be enough. But I mean, this proof, one needs to work a little harder.
Okay, thanks.
Yeah. Great. Let me think about it for a second. Yeah, I think the same kind of proof you can pretty cheaply get 2 times the arithmetic genus, but I think you don't quite need that many. Okay, so maybe let me just state a few more results which I think are important to know. So theorem. So X as above. Then we have this map from the geometric generic fiber of X, from pi1 of the geometric generic fiber of X to pi1 of the geometric special fiber of X. So this induces an isomorphism on prime to P completions. Where here P is the residue characteristic. You should look in SGA1 for the proof of this. It's actually not that bad. I mean, the main input is Abiancar's lemma, but we're not going to use it, so I'm not going to prove it. All right. So in fact, this gives us much finer information about these groups. So for example, it gives you an actual presentation of the prime to P completion of the fundamental group of a curve and positive characteristic. And again, this is something that we only know how to prove via analytic means. Okay, and so a couple more remarks. So remark, so there are analogous theorems for non-proper varieties with an S and C compactification, with a simple normal crossings compactification. So they're substantially harder. And moreover, one can say things beyond the prime to P completion. So the reference, and I encourage you to take a look at this, is Grothendieck Murr. There are analogous theorems for this for the so-called tame fundamental group. So this is a group associated to the category of finite étale covers of X, which are tame along the boundary of a simple normal crossings compactification, and more or less everything I've said. So if one can, for example, replace this prime to P completion with what one gets a surjection onto the tame fundamental group.
What is a simple normal crossings compactification?
So étale locally looks like the coordinate planes in affine space.
Okay.
Yeah. Great. Cool. So I think I just want to say one more thing about pi1, which is good because I'm almost out of time. So finally, I want to mention that there's a map. So there's a canonical map from continuous group cohomology of pi1 étale, x bar with any oh shoot. Okay, so first of all, this is sort of a simple proposition. So there's an equivalence of categories between LCC sheaves on X étale, so locally constant constructible sheaves, and continuous pi1 modules. So finite continuous pi1 étale modules. Okay, and what's the proof? Well, to go from right to left, a finite continuous pi1 module is in particular a finite continuous pi1 set. So it gives you a covering space, which gives you an LCC sheaf. Okay, and then vice versa. So LCC sheaves are represented by finite étale covers, is the proof. And I told you earlier that constructible sheaves are represented by quasi-finite morphisms. And so one needs to check a little bit that being LCC implies that those quasi-finite things are in fact finite étale. But you can also just prove this directly. So an LCC sheaf is locally constant by definition, while a constant sheaf is represented by a finite étale thing. And then you need to use the sheaf condition to glue. Okay. So finally, there's a canonical map. So given, so let me give this functor a name. So given M, I'm gonna send it to the LCC sheaf F sub M. So there's a canonical map from continuous group cohomology with coefficients in a pi1 module M to hi of x étale with coefficients in the sheaf Fm. And the theorem is that this induces an isomorphism on H0 and H1. Here X is connected. All right. So can anyone tell me what is the proof?
Sorry, what was FM?
Sorry, in this very rapidly stated proposition here, I said there was an equivalence of categories between finite pi1 modules and LCC sheaves, sending a finite pi1 module M to an LCC sheaf FM. Great. All right, so let me briefly explain why this is true. So morally, this is this is the same as the following topological situation. If you have a space X, like a semi-locally simply connected space X, it has a covering space, which is a pi1 torsor. So in other words, it maps to B pi1, and this is the pullback on cohomology. All right. So this comes from a morphism of sites from X8 to the site finite étale of X, where here covers are just covers. So what is this morphism of sites?
Inclusion.
Yeah, it's just inclusion. So it's a functor going the other way. A finite étale morphism is an étale morphism. So this induces a functor. Let me call this F. So the claim is that sheaves on the finite étale site are the same as pi1 étale sets. Great. And then the claim is that Fm is just F upper star of M under this isomorphism. And then finally, we need to show that the content is that R1 F lower star of a locally constant sheaf Fm is equal to 0. Okay. So let me just briefly so these two things I'm going to leave as an exercise because we're out of time. And you should ask me about it next time if you have trouble with it. So what's the content of this? The content of this is that if you have a cohomology class with coefficients in an LCC sheaf, you can kill it by a finite étale cover. Okay, but that we already know how to do. Such a cohomology class is a torsor, and a torsor kills the class of itself. So that's the proof. So this is the slogan of this last statement, is that torsors kill themselves. All right, and with that, they're out of time. Because I went extremely fast today, maybe I'll stop recording and stay for a few minutes